This video is sponsored by World of Warships.
As we stare out at the great wilderness that is the Milky Way galaxy, one thing stands out. We see no one else, at least so far. This has led to one of the more intriguing and perhaps even probable solutions to the Fermi Paradox, that we humans are very early in the game, and have only just appeared right at the time that such a civilization is possible in the galaxy. This idea that there is, or was, something out there that simply reset any surface life on exoplanets up until this point, that has since declined in frequency enough for us to exist, is one of the solutions that's gaining traction within astrobiology. My guest today has advanced just such a solution, that GammaRay Bursts may have been the culprit, and as they decline, we may see a blossoming of intelligence in the universe as it finally becomes safe for intelligent life.
You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. James Annis. Dr. Annis is a senior scientist at the Center for Particle Astrophysics at the Fermi National Accelerator Laboratory. His current research is measuring the parameters of the cosmology model using clusters of galaxies, the weak lensing they cause, and their effect on the cosmic microwave background. His research also includes measuring the local expansion rate of the universe using optical observations of gravitational wave sources. He joined the Sloan Digital Sky Survey in 1993 as a postdoc. He helped found the Dark Energy Survey in 2003.
James Annis, welcome to the program.
Well, thank you. Thanks for inviting me.
Now, Jim, in 1999, you authored a paper detailing a solution to the Fermi Paradox, one of many, which, there's I've heard of tens and tens of solutions to this. But yours is interesting because it's astrophysical in nature and says that, well, maybe there was something, GammaRay bursts, present in the universe that made it dangerous, and that intelligent life was not possible here until now, or not possible in the Milky Way at large. Can you give us an overview of that?
Sure. I'm going to start with the Fermi Paradox. I know your listeners have heard this before, but it's the starting place, and it leads me into the question of time. So the Fermi Paradox essentially is that the galaxy is quite old, 10,000 million years. But it doesn't take very long for a spacefaring civilization to go across it at any decent speed. Even Earth orbital speeds takes maybe 10,000 years to get to the next star over. That sounds like a long time, but that's not a long time to cross the galaxy. To cross the galaxy takes 100 million years. And we're not used to thinking about time in that way. We're not very good at it. The astronomers are, but the astronomers tend to work in units where the number is one, like one age of the universe, or 1 billion years. I'm going to work in millions of years because a million years is the lifespan of the most massive star, and it's the lifespan of a species. It's kind of the right time scale for this problem. And in this problem, if it takes 100 million years to cross the galaxy, but the galaxy is 10,000 million years old, that's practically no time at all. If intelligent life becomes a spacefaring civilization, then it should cross the galaxy like a wildfire seen by the galaxy. And that's a problem because there's not a whole lot of evidence that ever happened. Our idea of what time is based on human timescales, a century. A century is long if we're looking for the proof of some theory. But in astronomy, a million years is nothing. It just doesn't mean anything to us. 100 million years is getting there. Like the galaxy takes 200 million years to rotate. That might not be relevant, but it is. If you're just diffusing across the galaxy, star by star, because that's what you do as a spacefaring race, the galaxy rotation itself will smear out your culture, your planets that you have reached, the stars you have seen, in a smear pattern around the whole thing in 200 million years. It's just pretty easy for a spacefaring civilization to cover a galaxy in a short amount of time.
Yet we see absolutely no evidence that it has. You know, the solar system appears to be exactly as it formed. You know, we look out, so far we don't see radio signals, we don't see giant alien megastructures, no evidence of anyone out there. And this has been called the Great Silence, that we simply see no evidence of anyone except ourselves.
It's remarkably natural looking, very wild looking out there. I mean, it may be a bit underappreciated. If you look around the solar system, it's more than, it doesn't look like there's evidence for it. I mean, these days, people are looking for single probes. Or this great idea I heard was to use lunar orbiter data to go looking for a non-Apollo artifact on the moon. You know, there'll be Soviet spacecraft, there'll be a Chinese spacecraft. Is there anything else you can see? But you have to understand, on a million-year timescale, if there were aliens that had moved through the solar system and were here for 1 million years, the solar system would look nothing like what we're seeing. It would be engineered, it'd be tamed, it would look vastly different than rubble piles that we see from the moon to most of the asteroids. You know, the most exotic thing in the solar system might be Miranda, and even that looks like a reconstituted rubble pile. And if you move out into the rest of the galaxy, it's the same thing. It just looks natural. And I mean, I'm an observer. I study galaxies by trade, by craft. That's what I've been doing for my entire career. As observers, we have a whole bunch of these exotic galaxies. We keep them in our pockets, we talk about them. One is Hoag's object, and it's this giant ring of gas and stars around the galaxy. And there are things called polar ring galaxies. That's more stars around the ring galaxy, and that's like NGC 660 to give you a code number, which you can Google and see these things. You look at them, and they look natural. They don't look engineered, even though they're exotic galaxies. There's this great galaxy in Virgo. If you look at it, it's NGC 4753. You go look in the center of it, has these dust lanes, but dust lanes, even they look like a Lissajous pattern. But it turns out to be really easy to produce when you throw galaxies at each other. When we look around, you know, as a scientist, we want to interpret everything as natural, and we do that well. But if you just look at the images, the solar system, the galaxy, the nearest galaxies, they all look wild and natural, like they've not been touched by engineers.
Now, to flip that around, what would you expect an altered galaxy to look like?
Well, the classic one is that you imagine a civilization that wants to use starlight to power whatever endeavor it's up to. Dyson actually imagined just putting Earth around stars and just having Earth-like planets taking up most of the light from a star. You could do that over most of a galaxy, and then you get a dim galaxy that had the normal mass and have a lot of waste heat coming out around 273 Kelvin. We don't see those. We've looked. Jason Wright did this great search for dim galaxies with waste heat and didn't find a single one.
Now, is it possible, too, though, that there are certain types of galaxies that just would not be habitable? Is that an option? That maybe perhaps a majority of galaxies just couldn't even have a civilization because of too much radiation or something along those lines?
Putting aside explosions for the second, it doesn't look to me like most galaxies are very different than our galaxy. And in our galaxy, it looks to be a wide range of galactic-centric radii are fine for habitable planets and therefore for life-bearing places. I sort of don't think that we are in position to rule out habitable planets in galaxies. That's just sort of a lack of imagination in my point of view.
Now, in your paper, you go into the idea that maybe everything up until this point was simply getting sterilized, presumably by gamma-ray bursts. Can you go into that?
Sure, I'd be happy to. So we're back to this timescale issue. The galaxy is 10,000 million years old, and it only takes 100 million years to basically fill it up if you're moving at anything like space velocities of 0.1 or 0.01 c. So that suggests that if life forms anywhere, and that it's easy therefore to make intelligent life and spacefaring life, then the galaxy should be full of spacefaring civilizations. We don't see that. So you have a timescale problem. How do you cut the timescales down? How do you cut 10,000 million years down to at a couple hundred million years, maybe a billion years, 1,000 million years? That is not unreasonably done. You were getting at the idea of a galactic habitability zone. It has to do with the production of metal-rich stars. In my point of view, metal-rich stars formed super early in elliptical galaxies in the first billion years. And the bulk of star formation universes in the first 2,000, 3,000 million years. So for life in galaxies universe, it's still 10,000 million years. So how do you cut that timescale down? If you could cut that timescale down, then you might have a solution to the great silence, the Fermi Paradox. One approach is to imagine explosions do it. Supernova were thought of first. Supernova is either where a star collapses innards, it collapses to a neutron star or a black hole, and the outskirts blow up. Or there's mass transfer from a star to a white dwarf, which then detonates. Those aren't anywhere near powerful enough to affect anything more than a local regime, a few hundred light years at most. But gamma-ray bursts could do it. Gamma-ray bursts are as energetic as supernovae, but they don't produce the energy in neutrinos like supernovae do. They produce the energy as a beam jet. A beam jet of energy has lots of features to it, not least which is a long-term travel at high energy density. A high energy density jet could be considered a weapon, in fact. You could consider a weapon to wipe out life in star systems across tens of thousands of light years. Tens of thousands of light years is a galaxy scale. Now, so if you imagine gamma-ray bursts can sterilize planets, that's a big if, we have to come back to that, then you must start talking about, well, do they happen, how often do they happen? If they're once per galaxy per 10,000 million years, that's not sufficient. That's too rare. But it turns out that almost every scenario for a gamma-ray burst, usually they're young stars, current scenarios involve young stars, magnetars, follow the star formation history of the universe. The star formation history of the universe was mapped out about 20 years ago. And it's known that most stars were formed in the universe at about 2,000, 3,000 gigayears. There's an echo effect. There may be a delay time between when the stars were formed and a gamma-ray burst forms. The short gamma-ray bursts are almost certainly neutron star mergers, almost certainly in all cases. They may have a few thousand million year delay time, but the long gamma-ray bursts, the ones we're really talking about, almost certainly follow the star formation history. Now, our galaxy is still forming stars at about 1 solar mass per year. So star formation is still ongoing. It's just a lot lower than it was 10,000 million years ago. If gamma-ray bursts follow that, they were much more common in the early universe and much less common recently. One reasonable model gives a rate of about 1 per galaxy per 100 million years. Now that's the right time scale. Now we're talking. If gamma-ray bursts can sterilize large sections of a galaxy once every 100 million years, then you have a way to cut the time span down. Instead of 10,000 million years to fill a galaxy, you might have 100 million years to fill a galaxy. Then it's dicey if any galaxy will have a reasonable galactic spanning life, spacefaring life. So that's the heart of this. We need to talk about where the gamma-ray burst can actually do this. But in my mind, this is like another scientific endeavor in which there is a great scenario without a good mechanism. That's inflation. Inflation is this thing that happens in the early universe, where soon, actually well before the formation of elements, the universe expands at greater than light speed, and quantum fluctuations are blown up into large-scale structure in our universe. That solves the geometry of the universe. It makes it nice and Euclidean, flat. It solves homogeneity of the universe. Why is it the same in every direction as we look? Isotropic in the universe. And it's a standard feature of modern cosmology, but there's no known mechanism to cause it. There's no known particle or field that causes inflation. It's a scenario looking for a mechanism. And in my mind, this astrobiological phase transition model that we're talking about is rather like that. If there is a mechanism to suppress the formation of spacefaring civilizations until that slowly decays the universe, so that the mean time between suppressions after eons becomes long compared to how long it takes for life to become complex enough to form intelligent life and then to form spacefaring life, then you have a mechanism to explain the Great Silence. And gamma-ray bursts are the leading idea for it, but they're not a very successful idea for it. It'd be great. They're very energetic. They're very nice, but in detail, it doesn't quite work, and we can go into that.
Now, before we do that, this idea of sterilizing a planet. Now, could a gamma-ray burst, if sufficiently close, actually sterilize a planet, or is this more of a question of atmosphere? You're destroying an ozone layer, like with Earth or something like that. What is the way that the gamma-ray burst would actually cause an extinction?
The easiest way is to knock out the ozone layer. And then you get UV photons, and you let the UV photons from the sun actually just kill off life on the surface. That wouldn't kill sea-based life, but it would certainly kill anything that was in the photon field from a G star. So stars like ours would kill off life. It may not be true for the redder stars, the cooler stars. They may not have enough UV photons to actually do that. A secondary way is the jets themselves. The gamma-ray burst jets have enough energetic particles to cause a muon cascade in the atmosphere, and the muons can cause lethal damage. That's less likely. So does it really sterilize a planet? No, it just doesn't. Maybe the muon flux would, but the idea that gamma-ray burst jets can cause a muon shower in the atmosphere relies on closer proximity to the gamma-ray burst than the gamma-ray burst jets knocking out the ozone layer. It's a little bit less like it. Just turning off the UV flux, allowing the UV flux from the sun to hit our ecosystem would have disastrous consequences for animals on the surface. Probably maybe for the shallows in the ocean, but that would do nothing to the Deepsea Vents, for example. So sterilizing is a strong word.
That's interesting, because then say the people that are looking at exoplanets and say, as we move further with better equipment like the James Webb Telescope and such, and we can start trying to characterize these worlds, wouldn't it make more sense to look at worlds that have a lot of liquid water, an ocean, meaning that there's more survivability for life on a planet with a lot of ocean space, as opposed to, say, just a lot of land masses? Wouldn't it make sense to look at that, because those planets would be favored to have life that survived the gamma-ray bursts?
Yes, but there's lots of reasons to favor ocean worlds. Water is great for life. I mean, you don't need to reach for gamma-ray bursts being a problem for ground-based life. So back to deep sea vents. Deep sea vents are great, right? I mean, they're warm, they're nutrient-rich, and life likes them on the Earth. The odds of them being on Enceladus or Europa are really high. And that's the most likely scenario for life on those two moons. There's lots of reasons to look for icy planet or for ocean-bearing planets.
Now that's interesting. If you have that scenario, ice shell worlds like Europa and Enceladus, they would be impervious to gamma-ray bursts, wouldn't they? I mean, getting through that ice, they would just see no effect at all, right?
Well, there's no ozone layer to knock out, for example.
Nothing.
The muon shower could probably do it, but it depends on details. What I can't report on is the detailed structure of a jet from a gamma-ray burst, what kind of particle flux it produces, and whether that would cause a muon shower in the atmosphere or on the ice world. We just don't understand those jets well enough yet.
Now, this all leads to an explosion of intelligence in the future, starting effectively now. So we could end up with a universe that the older it gets, the more intelligent it gets, as far as civilizations spanning it. So is there anything that you can think of that would get in the way of that? Meaning that are the gamma-ray bursts just going to continue to get more and more sparse, or at least the ones the type we're talking about, the longer gamma-ray burst?
Gamma-ray bursts are getting rare, and they're becoming less luminous. Everything about them goes in the right direction. So if they are the suppression field, if there is so in my mental model of this, they're not really sterilizing planets. Gamma-ray bursts are really good at killing off ground-based life. They're not so great at killing off ocean-based life. And so it's in Earth's history, it's common for animals to migrate species by species from the ocean to land, back to the ocean and back to the land. Species just do that over tens of millions of years. It seems to me that a gamma-ray burst in Earth's prior history would be a mass extinction, and the ground-based stuff would just be repopulated from the oceans. So the fact that they're becoming more rare and less powerful just suggests that the ecosystems on the land have enough time to grow, fill the niches, explore the more outlandish body plans, find out new things that work as life does in the general ecological and evolutionary system. So it's pretty clear looking at life on Earth that it's getting more and more complicated. So you have to avoid the idea of progress or better, but being complicated isn't necessarily better. But it looks like life on Earth is getting more and more complicated. From one cell to multi-celled, from sponges to plants to animals. The one idea I really loved back in the late 90s was this idea that the more complex phyla can support larger and larger organisms. And so one can go back to the fossil record and look at the sizes of the largest animals in any given epoch and geological time. And it turns out the largest one is the blue whale. I mean, it's alive now. It's a mammal. It wasn't a dinosaur, and certainly wasn't an amphibian or a fish. As a metric for complexity, you have a thing in the geological record that lets you see complexity rising, as well as just looking at the body layouts of the more exotic creatures that existed in each geological epoch. So this idea that complexity is getting more in the universe, and that's anti-entropic. The life seems to be anti-entropic. So what are we left with? We are left with this idea that there's a suppression field that resets a clock, evolutionary clock, over and over again, while in the ocean, say, phyla are getting more complicated. At least they're like on Earth, they grew fish. Fish were more complicated than the worms and the other low forms, using a bad terminology, that existed. Until the suppression field became longer than a couple 100 million years. And then the land creatures would start to get large and complex. In my paper, I was enthralled with this idea that dinosaurs and all the reptiles that were associated with that class were extremely successful. They lasted for 200 million years, and they filled every single ecological niche you could imagine. They may or not have been intelligent, but they certainly didn't produce a civilization that could modify the environment in any kind of big way. And mammals lived with them for 100 million years, and they really didn't do anything well. The dinosaurs filled most of the niches, and the mammals filled small niches, burrowing niches, scavenger niches. But when an asteroid strike took out the dinosaurs, volcanism, asteroids, and bad luck took out the dinosaurs, and mammals could actually explore all the different ecological niches and explore body plans and explore how to survive, they got more complicated. And it only took 70 million years to come up with primates, and primates led to our intelligence. Not 100 million, but 70 million, which I find interesting. Now, our primate intelligence isn't the only way to get at intelligence. I've heard you mention before, and I certainly is by octopi. They're really smart, and they're mollusks. They're nothing to do with primates. They don't even have a vertebrae. Completely different phylum, but they're plenty smart. But they don't look like they're going to produce a metal smelting industry anytime in the next million years. It just doesn't seem to be what they're designed for.
Which that's another solution to the Fermi Paradox, is that most life is locked in oceans. It might be very intelligent, but it's stuck there because it can't launch rockets.
It can't launch rockets. Now, we're on the high end of terrestrial planet scale, so we're close to the edge of being able to launch rockets, but we're able to do it. I don't know. I mean, to me, we have at least 3 different classes of very intelligent creatures on Earth. There's primates, there's birds, and there's octopi. It seems to me that intelligent life is pretty easy to form. And then we get into what intelligence means. For the purpose of this conversation is, can we make spacecraft? And we haven't gotten out of the solar system yet, other than with probes.
Now, this idea that you mentioned, that life is antientropic, meaning that it gets more complex as time goes on, at least if with our sampling of one here on Earth, that begs a question. What does life end up at? What is Earth going to look like 100 million years from now, especially with a technological civilization on it that can alter evolution? So could it simply be that the solution to the Fermi Paradox is that once you get to a certain level of complexity, you become unrecognizable as life?
Sure. I mean, so whenever I hear this kind of argument, I mean, it's absolutely respectable and it makes absolute sense. I'm just left with, so you're a spacefaring civilization, you start moving out to different stars. After 1 million years, your species evolves to different species, probably in all directions. So now you have a big diversity of species. Maybe most of them go that way. Maybe most of them become crystalline structures that don't need to move and aren't really visible by electromagnetic means. But it only takes a few to keep on this path of growing through the galaxy, so that it's such that you would see them. I mean, the thing that we're looking for may not even be the average spacefaring civilization. It's just the ones that are expanding. Who is this? I think it was Servovic has this idea. No, it's Jason Wright. He has this idea that we get into this monocultural fallacy. We think of basically the British Empire taking over the galaxy. And really, it would be, even if it started off as one species, by the time it got halfway around the galaxy, it'd be many, 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 many species, probably pursuing different ends, each one a different end, in different ways.
And at some point, it becomes difficult to tell what is a different species, because if you have a civilization that's genetically modifying itself, or it's creating custom genetics completely out of nowhere, you start to lose the ability of being able to tell what is actually alien or what was once related to you at some point. Especially as you go out into the galaxy, this gets much worse over time.
If you go talk to paleontologists, they have a hard time understanding species on Earth. They're not static things. They're not well defined. They merge into each other. We're just saying that technologically you can make that much more interesting.
Absolutely. And you could end up, say humans head out into the galaxy and settle it over, X million years. Then they stay isolated from each other because of distance, eventually you can't really tell, 100 million years from now, you can't really tell that you're related to this other species that's halfway across the galaxy.
So this million-year time scale, species are about million-year time scales, and I don't think I can imagine humans being humans after a million years. I think we'd just be something else. That's just how evolution works. Even if it's technologically driven, it'll be just different. But a million years, again, a million years. So if there was a million-year civilization in the solar system would look nothing like it does now. It's just too long. It'd be so engineered. I continue to be enthralled by how natural the whole galaxy looks.
Well, even in terms of simple resources, we look at the asteroids, the meteorites that are falling, and they're full of all sorts of really valuable stuff like iridium and different, platinum, things like that. If someone had been here, they probably would have taken that by now.
Yeah, yes, exactly. Or out in the Kuiper Belt where the water is. Yeah. So why am I riffing on this? We imagine a scenario where civilization is moving through the galaxy slowly, million-year timescales, and they're becoming different creatures as they move. Technologically and by genetic drift, they're becoming different things in all directions. And yet, they're really surviving for million-year timescales, they're using up the resources of the star systems they're going to. But most of the SETI and artifact community speaks of is of small probes, nanoprobes, things that don't consume resources or much. And that's just to get away from how natural this stuff looks. I'm not convinced. I'm not convinced that life that does, so on Earth, I'll come back to this. On Earth, life seems to have gone to every single niche that it can fill and then some. It keeps on trying to fill other niches over and over again, whether it's successful or not. And I just think that's what's going to go on in the galaxy too. And the fact that that's just not obvious is stunning. So that's why I'm drawn to this idea of a phase transition where the universe, this galaxy, may not have a billion years of spacefaring civilizations in it, but the odds of us being the first or the 0th or the only one is just nil. The Copernican principle is very strong in astronomy, this idea that we're on average just common. We're not special. We have no special place in the universe. We're not the result of special processes. The things that happen to get us here may be rolls of dice. And if you rewrite history, you'll get a different rolls of the dice. It doesn't mean that things like us are not easy to get to. Convergent evolution. So how can it be that the universe, that this galaxy could be full of things that are like Earth-based life forms, and yet we don't see the super long history of spacefaring civilizations? And that's the phase transition idea where there might have been life in the galaxy for 10 billion years, 5 billion years, 10,000 billion years. But spacefaring civilizations are new, relatively, because it took so long that complex life forms on the ground, complex life forms that can build metalworking tools, that can build spacecraft, that can start expanding through the galaxy slowly, that may take 100 million years. If you suppress things for every 10 million years for ever, and then finally becomes 100 million years or 300 million years, all of a sudden, all around the galaxy, those life forms on all these planets are starting learning how to express complexity in their genetic makeup and in their body plans. They could all be waking up, looking at the night sky, looking at the stars, saying, we need to go there. I wonder what we'll find when we get there. Just like we're doing. Maybe they happened 10,000 years ago. Maybe the first one in the galaxy was 100 million years ago, and it's halfway moving through the galaxy. That has certain issues. You might be able to see them by now. We haven't seen anything, but it's at least better than we're alone, which makes us exalted in some exotic way, which doesn't seem to be true of any physical process that we know of in the universe. Or we're the first, which seems also unlikely. We certainly can't be the last. So why are we in this pristine-looking galaxy? Well, phase transition, something that suppresses spacefaring civilizations.
Sort of reminds one of Star Trek, where everybody's starting out and heading out at roughly the same technological level, and maybe somebody might be a little bit more advanced, but maybe not, and then lots of people would be less advanced, and and so on, so that it's sort of this awakening period in the Milky Way where everybody finally can achieve intelligence on suitable worlds and begin to head out. But this sort of bolsters the case for SETI, because if somebody else is just discovering radio, and saying, well, let's send a signal out there, then, this might be the time to look for that.
Exactly. I mean, there is a timescale argument. There's problems if civilizations, on average last for 10,000 years, then when you're looking, they may not be transmitting in the radio. But those are all problems that are technical and can be worked on. Given enough stars, looking enough places, you're going to find them by average anyway. It's a real strong argument for doing this traditional SETI work that, we've been doing for 50 years.
Now, you also mentioned, too, that nature doesn't really like anything that's unique. And, usually you always find examples of, you find something and then you find other examples of it. Stars doing strange things or whatever. It would seem really, really odd if we were alone, because we would be a one-off. And nature really doesn't seem to like that sort of thing. So that alone would suggest that the Fermi Paradox solution is that, no, there's life everywhere. It's just that its intelligence is merely rare, or at least right now. Now, regarding extinctions, though, through gamma-ray bursts, as I recall, one of Earth's extinction events, may have been a gamma-ray burst. That's on the table for having been a cause, because apparently much of the planet was sterilized to a few meters down in the ocean, and anything that was deep lived, but anything that was shallow did not. So is there any other examples of mass extinctions in Earth's history where maybe a gamma-ray burst was involved?
Well, that would be the most recent one. I think that's a Permian extinction event. And that was a couple 100 million years ago. Before that, it's ocean-based. And so there isn't, what are you looking for? You're looking for a die-off in the shallows in the oceans. No, I'm not aware of it. It's worth reminding ourselves that the dinosaurs were killed by an extraterrestrial event. And gamma-ray bursts are one of many extraterrestrial events that can affect us here on Earth. Solar flares, giant solar flares could present a real problem.
Especially to a technological civilization.
Even to not. So mass extinctions tend to wipe out the larger creatures. What you're left with are mice, if you're lucky. And it takes a long time to build back up from that, tens of millions of years. I can't think of another. In my mind, the Permian's the best candidate for a mass extinction caused by gamma-ray bursts, because it did have that kind of feature where all the land-based and a lot of the sea-based animals died off. But the other mass extinctions, there have been 5 mass extinctions, 4 mass extinctions, had the feature that they killed off most land-based creatures, but not all. And slowly the ecosystem regained its complexity and the niches got filled again. I'm okay with that. I'm not sure. Gamma-ray bursts are just sort of rare. They're and supernova are less rare, but they're not. They have to be a lot closer to cause damage. So following the way I tend to think, what would be the evidence you're looking for? And in asteroid strikes, it's the iridium layer that gives you the evidence that there was something from outside the Earth that causes, as opposed to volcanoes. Gamma-ray bursts and supernovae. Supernovae might give you radioactive tracers on asteroids that one could look for. The gamma-ray bursts, it depends a lot on what the jet looks like, what the details of the jet particle structure is, and what they do when they interact with matter. So my guess is we'd want to go probably to the ice balls, but maybe to the rocks, either the comets or the asteroids, and start looking at them, looking at the surface layers versus the deep layers, and see if you can find traces of events in them. There's this new dark matter model, right? People are looking for dark matter by looking at fossils, by looking at old rocks. It's an idea that has come back to fruition, and that we might actually gain some technologies from the darkness that would allow us to touch this.
That was actually of great interest to me, is the idea that you can study dark matter looking at minerals. Now, my last question for you is, could we still get hit by a gamma-ray burst? Is this still a threat to us? Could we go extinct if one of these were to go off nearby?
The simple answer is yes. The odds are low. The odds are always low for that kind of thing. But they're just a lot less common now than they used to be. You have to get unlucky. So my money on an extinction event for humans wouldn't rely on a gamma-ray burst. It'd probably be more like a solar flare.
Is it possible... Now, solar flare, of course, is a completely different animal, but is it possible for a civilization to shield itself from a gamma-ray burst should they know that these two neutron stars or whatever are going to merge? If they have sufficient time, can you avoid extinction?
Sure. So, yes. So that's one of the features of the model I put together. You have to do it before you get Kardashev Type 3 civilizations. Things that can harness any large fraction of a stellar energy or a galaxy's energy almost certainly can shield themselves. Get on one side of the planet, burrow down. If you're spacefaring, you can just leave the area. May take a while. You can have, assuming arbitrarily advanced technology, then you can reproduce yourself, if not your memories, reproduce yourself by using genetic technologies. So you put yourself in the ground in a genetic form and in a database form, wait for, a million years, and then reconstitute yourself and upload you from the database. So what you have to do is suppress civilizations before they get that advanced. You have to make sure you don't get that happening 5,000 million years ago so that you would see it all over the galaxy already. You must make sure that all spacefaring civilizations get wiped out regularly all the time. Because once they form and they get this arbitrarily advanced technology, sure they can. They'll figure out some way.
Now that's a dangerous galaxy, because then if you have one top dog, presumably the earliest civilization, saying, we're going to suppress everybody, then you're in a completely different solution to the Fermi Paradox. This is more in the dark forest territory, where something is out there that just keeps everybody down. And I think that's actually even scarier than a gamma-ray burst.
Yeah, I think so too. I mean, the way I heard it phrased the first time was, in nature, youngins don't yell, they don't scream. They're very, very quiet. Human babies scream bloody murder because the humans are the biggest threat in the ecosystem, the apex predator in general. Humans in the local universe are acting like human babies. We're just shouting out into the universe like, here we are, look at us, aren't we great? No one else is doing that. It seems like that could be dangerous. I found that argument interesting and a little bit scary.
It's hard to imagine human civilization as a progenitor of life in the galaxy. We would be the great old ones, that so long as we haven't gone extinct, could end up the elder siblings in a future galactic community. Maybe we will be the intelligent, advanced, enlightened civilization that sorts out the problems of the galaxy. Some of these new species we may meet may be completely unrelated to us, or still others may be creations entirely of our own design, or even uplifts of creatures who, while otherwise intelligent, lack the physiology or ability for space travel, or even technology. What odd dreams of the future we face.
John, what are you doing?
I'm playing my favorite game. I haven't even loaded it and my boat's already sinking.
There are sponsors, aren't they, John?
I'm happy to say they are, because this is a game that I really love and enjoy. If you're into naval architecture history, which is my other great love besides science, or just a great game, this is perfect, and it's free to download and play. World of Warships is a free-to-play game for PC and Mac. Command some of history's most iconic ships and unlock new ships as you prepare to dominate the oceans. With over 300 detailed warships customizations and upgrades, frequent events, and weather, there's enough to satisfy players of all levels. My favorite ship to play is the USS Atlanta, but there are also destroyers, other cruisers, battleships, and carriers, each of them with their own mechanics and gameplay. Use the link in the description below with the code READYFORBATTLE2020 to get started with a free package of 700 doubloons, 1,000,000 credits, 7 days premium account, and the premium ship USS Charleston with stars and stripes camouflage, and the premium Japanese ship, Anna, pronounce that.
Ishizuchi, John.
Thank you.
You told me it was a tactical simulation, John.
What? It is. I'm being totally tactical. Wait. The boat's leaking again. Anna, we need towels.
Oh dear. Why is the opossum in the bathtub?
Throw him a flotation device. We need a pump or something.